diode. This is also one of the very important. So whatever diodes you're seeing after Zener diode is very important in application perspective. Okay, so this is called as tunnel or Esaki diode. It's a thin junction diode with exhibits negative resistance under forward bias condition. Thin junction diode. Thin junction means the depletion region is very thin. And which see the next line, it exhibits negative resistance. So there is nothing like negative resistance in reality. So we have resistance of values 1 kilo ohm, 10 kilo ohm, 5 kilo ohm. There is no resistance of value minus 1 kilo ohm, right? So what does the negative resistance mean is, by Ohm's law, V is proportional to I. So you write V is equal to IR. So when voltage is going to increase, current is also going to increase as per Ohm's law. But when you consider these negative resistance devices, when voltage is going to increase, the current is going to decrease. Or the reverse, when current is going to increase, the voltage is going to decrease. So the property is inverse. So they exhibit a property called as negative resistance. Negative resistance means V is proportional to I. But here V is proportional to 1 by I. When V is increasing, I is decreasing. Or when V is decreasing, I is increasing. So this reduction in current or voltage is modeled as a new parameter called as negative resistance. Okay, so don't think that negative resistance means there is a component with value minus 10 ohm. No, that is not logically correct. So when the voltage or current is varied, the corresponding voltage or current, it will increase or decrease in the opposite way. That is called as negative resistance. So normal PN junction diode has an impurity of 1 into 10 power 8. So for every 10 power 8 silicon atoms, I'll be adding 1 impurity. So with the amount of doping, the depletion region width will be around 5 micrometers, correct? So this potential barrier will prevent the flow of carriers from one side to another because there is a definite depletion region width available. But if I'm going to increase the doping level to 1 is to 10 power 3, the device characteristics are completely changed. First PN junction diode, then you have Zener diode, then you have tunnel diode. Regarding to doping, PN junction diode has very minimum doping. Zener diode has heavy doping. Tunnel diode has very heavy doping. Okay, so I'm going to dope the PN junction diode very heavily in the order of 1 is to 10 power. For every 1000 silicon or germanium atoms, I'm going to have 1 acceptor or donor impurity. But previously, you see, for every 10 power 8 silicon atoms only, I'm going to have 1 impurity. But here, for every 1000 atoms, I'm going to have an impurity. So I can say I'm going to very heavily dope my tunnel diode. So when I dope the device very heavily, the depletion region becomes in the order of angstrom. So it reduces from 5 micrometer to 100 angstrom. 1 angstrom is 10 power minus 10. So this becomes 10 power minus 8 meters. So in terms of micrometers, if you want to say, it is 0.01 micrometers. So from 5 micrometers, I have reduced the depletion region width to 0.01 micrometers, which is extremely thin and it looks like a straight line. That's all. The depletion region, when you represent that, it looks like a straight line because it is very thin. And how am I achieving this thin depletion region? It is just by very heavy doping of my P and N regions of my PN junction diode. So the depletion region is very thin. So what happens, instead of electrons crossing the depletion region or drifting, they start penetrating through the junction. Usually electrons will they will cross the depletion region using the available voltage, forward bias voltage, which are going to apply the diode, right? But here they penetrate into the region and come out easily because the depletion region width is very small. It is in the order of 0.01 micrometers. So this penetrating effect of electrons is called by a new term called as tunnel diode. So it is called as tunneling. And hence, high impurity PN junction devices are called as tunnel diode. Just because tunneling happens inside the PN junction diode, it is called as tunnel diode. Conventionally, inside PN junction diode, you will have drifting. When will drifting happen? When the doping level is very minimal. When you increase the doping level to a very heavy doping level, then instead of drifting, we'll be having what is called as tunneling effect. That is why these diodes are called as tunnel diodes. So the typical VI characteristics is shown here in the tunnel diode. Next page you can see. So as you increase the forward bias voltage, the current will increase from 0 to 2 milliamperes. It will reach a maximum and then it will start decreasing. And this decreasing, you see, as I'm increasing the voltage, this current is decreasing. So this is called as negative resistance region. It goes to a minimum again and then it starts increasing just like conventional PN junction diode. In reverse bias, you see, it will be constantly increasing in reverse bias. It is not like a normal diode. See, these dotted lines are going to be the characteristics of normal diode. The straight line is going to be the characteristics of a tunnel diode. So you can see this region from A to B is called as negative resistance region because as voltage is increasing, the current is decreasing. So which reduces your resistance. So this change of resistance value because of change in voltage is called as negative resistance characteristics of a tunnel diode. We'll see why this reduction in current is happening in the tunnel diode. So at first you can see the forward current will rise sharply as applied voltage is increased. But for PN junction diode, you know it will be always increasing. But here it is increasing till the point where it attains maximum. So also the reverse current is very, very large when compared to the PN junction because the depletion region is very, very thin, right? So even in reverse bias, the charge carriers can cross the junction very, very easily, contributing to enormous current in reverse bias. So the intersecting portion starts at a point on the curve peak. As when you increase the forward bias voltage beyond the point A, the current will drop, the current will reduce till a minimum is reached. That point is called as B. This is called as the valley voltage. So the peak point is called as the peak voltage and the minimum point is called as valley voltage. So peak voltage is 50 millivolt and the valley voltage is 300 millivolt. The peak current is 2 milliamperes, the valley current is 0.2 milliamperes. So the point where it attains maximum is called as peak, the point where it attains minimum is called as valley. So these terminologies you have to remember for tunnel diode. So after B, when you start increasing the voltage, the current will increase just like your PN junction diode. So there is a peak and a minimum point, and then afterwards it exhibits the characteristics of an ideal PN junction